In this video, we are going to talk about size exclusion chromatography. Now, this size exclusion chromatography, or it is also known as molecular sieve chromatography, separate molecules on the basis of their size and shape. Okay, molecules are separated on the basis of their size and shape in your size exclusion chromatography or molecular sieve chromatography. Now, in this technique, a column matrix is filled with porous gel beads. Now, these porous gel beads are made up of insoluble and hydrated polymer such as polyacrylamide, dextran and agarose. Okay, in this technique, we are using a column matrix filled with porous gel beads. The gel beads which we are using are made up of insoluble and hydrated polymer, and the example of that is polyacrylamide, that is cefacryl or biogel P, dextran, that is cefadex, or agarose, that is cefarose. Okay, so these three kind of insoluble and hydrated polymer are used to make this porous gel beads, and when the column matrix is filled with this porous gel beads, and this act as the stationary phase in your size exclusion chromatography. So the stationary phase of your size exclusion chromatography is a column matrix filled with porous gel beads made up of polyacrylamide or dextran or agarose. Now, this size exclusion chromatography includes gel permeation chromatography and gel filtration chromatography. Okay, these two, that is gel permeation chromatography and gel filtration chromatography, are included in your size exclusion chromatography. Now, this gel permeation chromatography uses organic mobile solvent, and this gel filtration chromatography uses aqueous mobile solvent to separate and characterize the molecules. Okay, the gel permeation chromatography is using organic mobile solvent, and gel filtration chromatography is using aqueous mobile solvent to separate and characterize the molecules. Now, the basis of this size exclusion chromatography is very simple. So, we take a solution which has molecules of various sizes and we pass that solution through the column. Now, that column have beads with pores. Okay, so the molecules which are smaller than pores will enter the pores of bead, and the larger molecules will not enter the pores of bead. Okay, you have a column. In that column you have beads, and that beads have pores, and you pass a solution of molecules of various sizes through that column, through that beads, through those pores, and because of that, the molecules which are smaller than pores will enter the pores of beads, and the larger molecules which are larger than the pores of bead will not enter the pores. And that is the reason why the larger molecule will move faster and will elute first, and the smaller molecules which have entered the pores of beads will take a longer path and will take a longer retention time as compared to larger molecules which cannot enter the pores. So this is how it looks. Okay, this is how your size exclusion chromatography is. So you have this column. Okay, this column is filled with beads which have pores. Now you fill the column with those beads and you put a mobile phase containing various molecules of various sizes. Okay, there are, let's consider these red ones are bigger ones, and these blue molecules are the smaller molecules, and we are comparing it with the size of the pores of the bead. So as the time passes, the larger molecules don't enter the bead, don't enter the pores of the bead, and that is the reason why they move faster. but these smaller molecules, these blue molecules, are smaller than the size of the pores, and that is the reason why they enter. Okay, so it can be understood in this diagram. Okay, so consider this is a bead and it have pores in it. Okay, so these larger molecules will not enter the pores because they are larger than the pores, but these smaller molecules will enter the pores. Okay, so these larger molecules have no resistance to go downward, and that is the reason why they move at a faster rate. But these small molecules, as they enter the pores, they will take more time to come out of the column. Okay, and that is what happens. Okay, after a considerable amount of time, these larger molecules come out through the column matrix, and these small molecules are retained. Smaller molecules will also come out eventually, but it will take a longer time. Okay, so this is how your size exclusion chromatography actually works. So if a mixture of protein is applied to the column, which we just saw, and washed with an appropriate buffer, then the first protein that will emerge out of the column will be too large to enter the pores of the gel beads. Okay, and the other remaining proteins will be eluted according to their decreasing size of the molecular weight. Okay, so as the molecular side will decrease, according to that they will be eluted out. Okay, so there you have a mixture of proteins. You apply those you put those mixture of proteins into this column with beads and wash it with appropriate buffer. The larger proteins will come out of the column first, and the smaller protein will eventually come out after that. The smaller the molecule, the more time it will take to come out. So that is how it is going to work. Now the molecular mass of the smallest molecule, which is unable to penetrate the pores of the given gel, is known as exclusion limit. Okay, what is exclusion limit? Exclusion limit is the molecular mass of the smallest molecule that is not able to penetrate. Okay, that is unable to penetrate the pores of the given gel. Okay, that is what your exclusion limit is. So this Cephadx have the exclusion limit of about 30,000 Dalton. So all the solute molecules whose molecular size is greater than 30,000 Dalton will pass directly through the column without entering the gel pores. So if your molecule have a molecular size less than 30,000 Dalton, then it will enter the pores of the Cephadx, and then it will take a longer time to separate, to come out of the matrix. Now for a given sample, the distribution coefficient, that is Kd, depends upon its size. So consider a molecule. Okay, if that molecule is completely excluded from the pore, then the distribution coefficient Kd for that molecule is 0. Okay, if the molecule is completely excluded by the pore, then the Kd is 0 for that molecule. But if the molecule is able to enter the porous bead and that molecule have accessibility to the inner solvent, then Kd for that molecule is 1. Okay, so if molecule is large and it cannot enter the pore, then the Kd for that molecule is 0. But if molecule is small enough to enter the pores of beads and it have the accessibility to the inner solvent, then the value of Kd for that particular molecule is 1. And for all other intermediates, the Kd varies from 0 to 1. So for larger molecule it is 0, for the smallest molecules it is 1, and all the intermediates, other molecules, it is from 0 to 1. Now let's discuss about the size measurements by size exclusion chromatography. Okay, by doing size exclusion chromatography, how can you measure the size of a particular molecule? Now, in order to obtain the information about the size of a particular solute by doing size exclusion chromatography experiments, the column that we are going to use in this experiment should be characterized in order of its volume that is accessible to the analytes. Okay, the column should be characterized if you want to obtain the size information of a particular solute by doing size exclusion chromatography experiment. Okay, the column should be characterized in accordance to its volume that is accessible to the analytes. Now, the total volume, which is represented by Vt of the size exclusion chromatography column, is divided into three parts. Okay, there are three parts of the total volume of this size exclusion chromatography column. Now, the first part is about the volume that is external to the packing material. Okay, the first part is the void volume, which is represented by V naught. Okay, this volume is external to the packaging material. Now, the second part is the volume that is contained by the porous beads, and this volume is accessible to the small molecules. Okay, this second part is known as internal volume, which is represented by Vi. Okay, so Vi is the volume that is contained within the porous beads, and this volume inside the porous beads is accessible to the small molecules. Okay, that is this type of volume is represented by Vi. And the third part of the total volume is the volume occupied by the packing material. Okay, and this volume is known as bed volume, which is represented by Vg. So Vt is, that is the total volume, is equal to void volume V0 plus internal volume Vi plus the bed volume Vg. Okay, this is how you get the total volume of the column that you are using in the size exclusion chromatography. Now, the volumes V0 and Vi, these are determined experimentally by measuring the elution volumes. Okay, so V0 is measured by measuring the elution volume of large solutes that is totally excluded from the interior of the porous bead, and Vi is measured by measuring the elution volume of the small solutes that has access to all pores of the gel beads. Okay, so if you measure the elution volume of the large solutes that are totally excluded from the interior of the porous bed, then on the basis of that you will get the volume of V0, you will get the value of V0, and if you measure the elution volumes of small solute that has access of the all pores of the gel bead, if you measure elution volume of this, then you will get the value of Vi. Okay, so the value of V0 and Vi is determined experimentally. Now, the elution volume of a given solute, that is Ve, is the volume of solvent that is required to elute the solute from the column when it is first contacted with the gel. Okay, Ve is the elution volume of a given solute, and Ve is the volume of solvent that is required to elute the solute from the column when that solute has first contacted with the gel. Now, the elution volume Ve of the solute that is partially included in the pores of gel beads can be related to void volume and internal volume by this equation, that is Ve, that is elution volume, is equal to void volume plus sigma into Vi, that is internal volume, and this sigma represents the partition coefficient of the solute. So, elution volume is equal to void volume plus sigma into internal volume. Now this partition coefficient sigma represents how much internal volume is available for the solute. Okay, how much internal volume is available for the solute, that is represented by this partition coefficient sigma. And the value of sigma is between 0 and 1. That is, it is greater than 0 but it is smaller than 1. Now when this sigma is compared with the values of the measured, which is measured for the solute of the known size, then that comparison gives the information about the molecular size of unknown solute. Okay, you compare this sigma of the unknown solute with the sigma of known solute, and then you will get the information about the molecular size of that unknown solute that you are doing experiment to find its size, molecular size. Okay, so you get this value of sigma of this unknown solute, and then you compare this sigma with the sigma of the other solutes whose size you know. Now if the series of solutes of known sizes are subjected to size exclusion chromatography, then you will find that there is a linear relationship between this partition coefficient and size. Okay, if you subject a series of solutes of known sizes with size exclusion chromatography, then you will find a linear relationship between the partition coefficient and the size. So yeah, you do size exclusion chromatography for a particular analyte, you find its partition coefficient, then you compare that partition coefficient with the partition coefficient of the other known size solute molecules, and that is how you determine the size of that particular solute by doing size exclusion chromatography. Okay, so that's all for this video. Thanks for watching and stay tuned.